Nearly 5 decades into its mission, Voyager 1 has begun transmitting scrambled data from interstellar space that has left NASA scientists completely baffled. The spacecraft, now positioned over 25 billion kilometers from Earth in 2025, recently started sending corrupted signals from its flight data subsystem that take 22 hours and 35 minutes to reach mission control. These mysterious transmissions represent the first time in 48 years that Voyager's instrument data has been so severely garbled, with the spacecraft's attitude control system reporting impossible readings while somehow maintaining perfect communication with Earth. What could be causing this unprecedented malfunction in a probe that has operated flawlessly for nearly half a century? The answer lies in understanding how this remarkable mission began, the genesis of humanity's greatest journey. In the mid-1970s, NASA engineers faced an extraordinary challenge that would push the boundaries of spacecraft design. They needed to build a probe capable of surviving a journey to the outer planets using technology that seemed primitive even by the standards of the day. Computer systems were basic, power sources unreliable over vast distances, and no spacecraft ever operated for more than a few years in deep space's harsh environment. The engineering team at the Jet Propulsion Laboratory had to create systems that could withstand temperature swings from 400 degrees Fahrenheit to minus 300 degrees Fahrenheit, survive cosmic radiation bombardment, and maintain precise pointing accuracy across billions of miles. The spacecraft's entire command memory would fit in under 70 kilobytes, less than a simple smartphone app today. Every component required redundant backup systems because repair missions were impossible once the probe left Earth orbit. NASA's ambitious plans centered on seizing a once-in-176-year opportunity. Astronomers had calculated that the outer planets would align in such a way that a spacecraft could slingshot past Jupiter, Saturn, Uranus, and Neptune on a single ride. This rare celestial arrangement would allow the probe to use each planet's gravity as a natural accelerator, dramatically reducing fuel requirements and travel time between targets. Without this alignment, separate missions to each planet would have taken decades and required massive rockets that didn't exist. The spacecraft that emerged from these design challenges weighed 1,592 pounds and stood 13 feet tall, roughly the size of a small car, including its extended antenna and scientific instruments. Engineers equipped it with a radioisotope thermoelectric generator that would convert heat from decaying plutonium into electricity, providing a steady power source that could theoretically operate for decades. The probe carried 11 scientific instruments designed to study magnetic fields, plasma particles, cosmic rays, and photograph planetary systems. Mission planners originally scheduled Voyager 1 for a primary mission lasting 4 years, with possible extended operations for another year or two if the spacecraft remained functional. The probe was designed to complete flybys of Jupiter and Saturn, photograph their moons, and gather scientific data before its systems would inevitably fail. Engineers built in some margin for extended operations, but they never seriously considered that the spacecraft might still be transmitting data in the 21st century. The launch window opened in August 1977, and NASA had only weeks to get both spacecraft into space before the planetary alignment would no longer support their planned trajectory. Voyager 2 launched first on August 20th, 1977, followed by Voyager 1 on September 5th, 1977. Despite launching second, Voyager 1 followed a faster trajectory that would allow it to reach Jupiter and Saturn ahead of its twin. The launch vehicles were Titan IIE rockets, among the most powerful available at the time. As Voyager 1 began its journey toward Jupiter, mission controllers started realizing they had built something far more durable than anticipated. The spacecraft's systems continued functioning flawlessly month after month. Its instruments remained calibrated, and its communication systems maintained clear contact with Earth across ever-increasing distances. The probe's nuclear power source performed better than predicted, and its computer systems showed no signs of degradation from prolonged cosmic radiation exposure. The transition from a temporary planetary exploration mission to humanity's longest-running space adventure happened gradually as Voyager 1 exceeded every performance milestone. What began as a 4-year mission to photograph Jupiter and Saturn evolved into an unprecedented journey toward interstellar space. Engineers started planning extended mission phases they had never seriously considered during the design process. By the 1980s, it became clear that Voyager 1 would continue operating long after completing its primary objectives. The spacecraft's trajectory was carrying it toward the edge of the solar system at 38,000 miles per hour, faster than any human-made object had ever traveled. Mission planners began envisioning scenarios where the probe might actually leave the solar system entirely and begin transmitting data from interstellar space. The spacecraft's remarkable longevity created new challenges its designers had never anticipated. Communication delays grew from minutes to hours as Voyager 1 traveled farther from Earth, making real-time control impossible. Ground controllers had to develop new procedures for managing a spacecraft that operated almost entirely autonomously, with commands taking over 20 hours to reach the probe and responses taking another 20 hours to return. As Voyager 1 approached its 48th year of operation in 2025, the gap between its original mission timeline and current reality had become almost surreal. A spacecraft designed to last 4 years was still transmitting scientific data from beyond the solar system, operating with 1970s technology in conditions its creators had never imagined. The probe's computer systems, memory storage, and scientific instruments were functioning in an environment where no Earth-based testing could have predicted their performance. The engineering success of Voyager 1's extended lifetime has made its recent signal anomalies even more puzzling for NASA scientists. After nearly 5 decades of reliable operation, the spacecraft that exceeded every expectation was about to embark on the most spectacular phase of its journey, racing toward encounters that would rewrite our understanding of the outer solar system. Racing through the outer solar system. Voyager 1 accelerated toward Jupiter at a velocity that stunned mission controllers who had calculated its trajectory months in advance. The spacecraft crossed the asteroid belt between Mars and Jupiter in early 1978, becoming the first human-made object to navigate this treacherous region of space debris and rocky fragments. Controllers at the Jet Propulsion Laboratory watched their screens as telemetry data confirmed the probe had survived the passage unscathed, its instruments still functioning perfectly despite traveling through an area where impacts from asteroids could have destroyed the mission instantly. The spacecraft transmitted its first images of Jupiter in April 1978 when it was still 160 million miles away from the giant planet. These early photographs revealed atmospheric details that ground-based telescopes had never captured, showing swirling storm systems and cloud patterns that extended far beyond what astronomers had predicted. As Voyager 1 approached Jupiter throughout 1979, culminating in its closest encounter on March 5, 1979, its cameras and scientific instruments began collecting data that contradicted decades of theoretical models about the planet's composition and behavior. The most shocking discovery came from Jupiter's moon system, particularly Io, which appeared in Voyager 1's cameras as a world covered with active volcanoes, contradicting every scientific prediction that small moons should be geologically dead. The spacecraft captured images of volcanic plumes shooting sulfur dioxide 190 miles above Io's surface, proving that tidal heating from Jupiter's massive gravitational pull was keeping the moon's interior molten and active. Scientists had expected to find a cold, cratered world similar to Earth's moon, but instead discovered the most volcanically active body in the solar system. The gravitational slingshot maneuver around Jupiter accelerated Voyager 1 to speeds that exceeded its original design specifications by thousands of miles per hour. The spacecraft used Jupiter's immense gravitational field as a natural accelerator, gaining velocity that would have required massive amounts of fuel to achieve through rocket propulsion alone. This technique allowed the probe to reach Saturn in just over a year instead of the multiple years that a direct trajectory would have required. Saturn's encounter. On November 12, 1980, revealed the ringed planet's atmosphere contained approximately 7% helium compared to Jupiter's 11% composition, while the ring system surrounding Saturn displayed intricate structures that ground-based telescopes had never resolved. Voyager 1's cameras revealed thousands of individual ringlets separated by gaps and divisions that created a complexity far beyond the simple ring system that astronomers had observed from Earth. The spacecraft discovered shepherd moons that gravitationally confined ring particles within specific orbital zones, explaining how Saturn maintained such well-defined ring boundaries over millions of years. Titan emerged as Saturn's most intriguing moon when Voyager 1's instruments penetrated the thick atmospheric haze that obscured the surface from view, detecting a dense nitrogen atmosphere with traces of methane and other organic compounds that created conditions where liquid hydrocarbons might pool in lakes and rivers across the moon's landscape. The Titan flyby trajectory required Voyager 1 to pass beneath Saturn's south pole, which permanently altered the spacecraft's path and ended its planetary exploration phase. This maneuver sent the probe out of the ecliptic plane contains most planetary orbits, directing it toward interstellar space at an angle that would carry it away from any future planetary encounters. Mission planners had designed this trajectory knowing it would sacrifice additional planetary science for the opportunity to study Titan's unique atmosphere. Communication systems maintained constant contact with Earth throughout these planetary encounters, despite distances that stretched across hundreds of millions of miles. The spacecraft's 12-foot diameter antenna transmitted data using frequencies of 2.3 gigahertz and 8.4 gigahertz, while ground controllers sent commands at 2.1 gigahertz through the Deep Space Network's massive radio dishes. Signal travel times increased from minutes to hours as Voyager 1 moved farther from Earth, creating operational challenges that required mission controllers to plan activities days in advance. Each planetary encounter pushed Voyager 1 deeper into uncharted regions of the solar system where no spacecraft had ever operated. The probe's trajectory was carrying it toward the outer boundary of the solar system at a velocity of 38,000 miles per hour, faster than any human-made object had ever traveled. Mission scientists began to realize that Voyager 1 might actually cross into interstellar space within a few decades, transforming a planetary exploration mission into humanity's first probe of the space between stars. The technological achievements demonstrated during these planetary flybys established Voyager 1 as the most successful deep space mission in history. The spacecraft's ability to maintain precise pointing accuracy while traveling at tremendous speeds allowed it to capture detailed images and scientific measurements that revolutionized planetary science. As the probe continued racing outward from Saturn, mission controllers tracked its progress toward regions of space where no human technology had ever ventured, wondering what discoveries awaited in the vast emptiness beyond the solar system's edge, breaking the ultimate barrier. By August 2012, Voyager 1 had traveled farther from Earth than any human-made object in history, but scientists still weren't certain whether the spacecraft had actually crossed the boundary that separates our solar system from interstellar space. The probe was operating in a region where solar wind particles from our sun collided with cosmic radiation from distant stars, creating a turbulent zone that made it difficult to determine exactly when the transition occurred. Mission controllers knew the spacecraft was approaching this critical threshold, but the boundary itself remained invisible to most of the probe's instruments. The heliopause represents the point where the solar wind from our sun loses its influence and gives way to the interstellar medium that fills the space between stars. Scientists had theoretical models about what this boundary should look like, but no spacecraft had ever approached it before to provide actual measurements. Voyager 1's instruments detected changes in the cosmic ray environment and solar wind behavior throughout 2011 and early 2012. But these changes were gradual rather than the dramatic shift that many researchers had expected. The definitive proof came from an unexpected source when Voyager 1's plasma wave instruments detected oscillations caused by a powerful solar eruption that had occurred months earlier. The spacecraft's plasma wave instrument measured the frequency of electron vibrations in the surrounding space, which revealed the density of charged particles in the immediate area. These measurements indicated that Voyager 1 was surrounded by a much denser plasma environment than anything detected within the solar system's protective bubble. Scientists analyzed the plasma wave data and calculated that the electron density around Voyager 1 was approximately 80 times higher than measurements taken just outside the heliopause boundary. This dramatic increase in particle density provided conclusive evidence that the spacecraft had entered a fundamentally different region of space where the influence of our sun's solar wind had been replaced by the interstellar medium. The plasma wave instrument had effectively become Voyager 1's compass for navigating the transition between solar and interstellar space. The official crossing date was determined to be August 25, 2012, when Voyager 1 was positioned 121 astronomical units from the Sun, equivalent to approximately 11.2 billion miles from Earth. At this distance, sunlight required 16.89 hours to reach the spacecraft, and radio signals took the same amount of time to travel between Voyager 1 and mission control on Earth. The probe was traveling at a velocity of 17.043 kilometers per second relative to the Sun, fast enough to cover the distance from New York to Los Angeles in under 4 minutes. The magnetic field measurements during the boundary crossing surprised scientists because they expected a dramatic change in field direction when Voyager 1 entered interstellar space. Instead, the magnetic field changed direction by only 2 degrees, indicating that the local interstellar magnetic field was aligned almost parallel to the solar magnetic field in that region. This unexpected finding revealed gaps in the scientific community's understanding of the heliopause boundary. Cosmic radiation levels increased dramatically after Voyager 1 crossed into interstellar space, with high-energy particles becoming approximately 100 times more abundant than measurements taken within the heliosphere. These cosmic rays originated from distant stars and galactic events, creating a radiation environment that was far more intense than anything the spacecraft had encountered during its journey through the solar system. The increased radiation levels posed potential risks to Voyager 1's electronic systems, which had been designed in the 1970s without consideration for such extreme conditions. The interstellar medium revealed itself to be a complex environment filled with gas and dust particles that had been expelled by dying stars throughout the galaxy's history. Voyager 1's instruments detected hydrogen atoms, helium particles, and heavier elements that formed a tenuous but measurable substance between stellar systems. The temperature of this interstellar material was surprisingly cold, measuring approximately 15,000 degrees Celsius, which was much cooler than the million-degree temperature of the solar wind that dominated space within the heliosphere. Communication delays continued to increase as Voyager 1 traveled deeper into interstellar space, reaching over 17 hours each way by the time the boundary crossing was confirmed. These extended delays meant that real-time control of the spacecraft became impossible, requiring mission controllers to plan operations days in advance and rely on Voyager 1's autonomous systems to handle any unexpected situations. The spacecraft had to operate independently for extended periods while commands and status updates crawled across the vast distances at the speed of light. The instruments aboard Voyager 1 had to adapt to measuring phenomena that their designers had never anticipated when the spacecraft was built in the 1970s. The cosmic ray detector, which was originally intended to study radiation near Jupiter and Saturn, became the primary tool for monitoring the interstellar radiation environment. The magnetometer, designed to measure planetary magnetic fields, now tracked the subtle variations in the interstellar magnetic field that pervades the space between stars. The transition into interstellar space fundamentally changed Voyager 1's mission from planetary exploration to galactic astronomy. Instead of studying individual worlds within our solar system, the spacecraft became humanity's first direct probe of the interstellar medium that connects our sun to the rest of the Milky Way galaxy. Scientists realized they now had access to measurements from a region of space that could only be studied through remote observations from Earth-based telescopes. The crossing into interstellar space marked the beginning of Voyager 1's most scientifically valuable phase, even though the spacecraft was operating with 1970s technology that had already exceeded its design lifetime by decades. Every day of continued operation provided unprecedented data about conditions in the local interstellar neighborhood that surrounded our solar system. As the years passed and Voyager 1 continued racing deeper into this uncharted territory, the distances involved would soon reach scales that challenged human comprehension and created unprecedented technical obstacles for mission controllers. The 2025 Distance Milestone. As of February 2025, Voyager 1 has reached a staggering distance of 24,475,900,000 kilometers from Earth, positioning itself 167.34 astronomical units away from our home planet. This distance means the spacecraft has traveled over 162 times the Earth-Sun distance, venturing into a region of space where no human technology has ever operated before. Light itself, traveling at 300,000 kilometers per second, requires 22 hours, 35 minutes, and 9.8 seconds to make the one-way trip between Voyager 1 and Earth. The spacecraft continues extending this record daily, adding approximately 523 million kilometers to its journey each year as it races deeper into interstellar space. Every single day that passes, Voyager 1 extends its record as the most distant human-made object ever created, covering roughly 1.4 million kilometers in its relentless journey into the void. The spacecraft travels through interstellar space at a velocity of 61,000 kilometers per hour, moving at speeds that would carry it around Earth's equator in less than 2 hours. At this incredible velocity, Voyager 1 advances 3.57 astronomical units farther from the Sun each year, yet the vastness of space means that neighboring star systems remain tens of thousands of years away, even at this remarkable pace. The communication delays created by this extreme distance have transformed every interaction with Voyager 1 into a carefully orchestrated exercise in patience and precision. When mission controllers at NASA's Jet Propulsion Laboratory send a command to the spacecraft, they must wait over 22 hours to confirm that their instructions were received and executed properly. This delay means that troubleshooting any problems becomes an incredibly slow process where each diagnostic step takes nearly 2 full days to complete. Engineers cannot simply flip a switch or restart a system like they might with satellites in Earth orbit. The mathematical precision required to maintain contact with Voyager 1 at such distances pushes the boundaries of human technological capability. NASA's Deep Space Network must account for the spacecraft's position with accuracy measured in arcseconds, which represents angles smaller than the width of a human hair viewed from 100 yards away. The radio signals sent to and from Voyager 1 must be aimed with extraordinary precision, because even the slightest error in pointing direction would cause the transmission to miss the spacecraft entirely and disappear into the cosmos. Ground controllers track Voyager 1's position using a combination of radio ranging measurements and Doppler shift analysis that can detect velocity changes as small as a fraction of a millimeter per second. The spacecraft's trajectory must be calculated accounting for gravitational influences from the Sun, planets, and even large asteroids that can slightly alter its path over time. These calculations require supercomputers to process the complex orbital mechanics involved in predicting where Voyager 1 will be located when signals finally reach its position. The Deep Space Network relies on massive radio dishes to communicate with Voyager 1, but only one antenna on Earth possesses enough signal power to send commands to the distant spacecraft. Deep Space Station 43 in Canberra, Australia, operates the sole 70-meter antenna capable of transmitting instructions across the 24.5 billion kilometer gap to Voyager 1. This single point of failure creates a critical vulnerability in maintaining contact with humanity's most distant explorer, especially when the antenna requires maintenance or upgrades that temporarily sever the communication link. Signal strength becomes another major challenge at Voyager 1's current distance, because radio waves spread out over increasingly large areas as they travel through space. The spacecraft's transmitter produces only 23 watts of power, roughly equivalent to a refrigerator light bulb. Yet this faint signal must travel across interstellar distances where it becomes billions of times weaker by the time it reaches Earth. The Deep Space Network's sensitive receivers can detect signals so weak that they carry less energy than a snowflake hitting the ground. Voyager 1's current position represents the absolute edge of human technological reach, operating in a region of space where no backup systems or rescue missions could ever provide assistance. The spacecraft functions completely autonomously for days at a time between communication sessions, relying on computer systems built with 1970s technology to make critical decisions about power management, antenna pointing, and scientific observations. These ancient computers must continue operating flawlessly in an environment where cosmic radiation and extreme temperatures pose constant threats to electronic systems. The extreme distance complicates understanding any unusual behavior because traditional troubleshooting methods become nearly impossible to implement. When engineers detect irregularities in Voyager 1 systems, they cannot simply run quick diagnostic tests or request immediate status updates like they would with closer spacecraft. Every attempt to gather additional information requires a minimum of 45 hours to send a command and receive a response, turning simple diagnostics into multi-day investigations. Temperature variations in interstellar space add another layer of complexity to maintaining Voyager 1's systems at such distances. The spacecraft experiences temperature swings that can affect the performance of electronic components in ways that are difficult to predict or compensate for remotely. Components that have operated reliably for decades might begin exhibiting subtle changes in behavior as they encounter conditions that were never tested during the original mission design phase in the 1970s. Power management becomes increasingly critical as Voyager 1 continues its journey deeper into interstellar space, because the spacecraft's nuclear power source produces less electricity each year. The radioisotope thermoelectric generator loses approximately 4 watts of power annually, forcing mission planners to make difficult decisions about which instruments to keep operational. Every diagnostic procedure requires careful consideration of power consumption, because unnecessary operations could shorten the mission's remaining lifespan. The record-breaking distance achieved by Voyager 1 in 2025 has created an unprecedented situation where humanity's most advanced 1970s technology operates in complete isolation at the very limits of our communication capabilities. No other human-made object has ever functioned at such extreme ranges, making any unusual behavior particularly challenging to diagnose because engineers have no comparable experience to guide their troubleshooting efforts. Against this backdrop of extreme isolation and technical complexity, mission controllers began noticing subtle changes in the space when signals turned strange. The first hints that something unusual was happening with Voyager 1's communications appeared in late 2023 when mission controllers at NASA's Jet Propulsion Laboratory noticed subtle irregularities in the data streams arriving from the distant spacecraft. These initial anomalies were minor, enough that engineers attributed them to the normal wear and tear expected from a 46-year-old spacecraft operating in the harsh environment of interstellar space. The probe had encountered occasional glitches throughout its decades-long journey, and most had resolved themselves or been corrected through routine troubleshooting procedures that had worked reliably for years. Engineers monitoring Voyager 1's telemetry data observed that certain measurements were arriving with timing inconsistencies that hadn't been present in previous transmissions. The spacecraft's flight data subsystem, known as the FDS, which packages all scientific and engineering information before transmission to Earth, began producing outputs that contained unexpected patterns mixed in with the normal data streams. These early warning signs were subtle enough that they might have been dismissed as temporary fluctuations caused by cosmic radiation or temperature variations in the spacecraft's aging electronics. The situation escalated dramatically in November 2023 when Voyager 1's communications with Earth became severely disrupted as the spacecraft began transmitting a monotonous sequence of ones and zeros instead of its usual scientific data. This repeating binary pattern rendered the probe's transmissions completely unreadable, preventing mission scientists from accessing the valuable interstellar measurements that Voyager 1 had been collecting during its journey through space beyond the solar system. Instead of receiving complex scientific observations about cosmic radiation, magnetic field measurements, and particle densities in interstellar space, ground controllers found themselves listening to what one engineer described as a monotonous dial tone that provided no useful information. The technical systems affected by these mysterious transmissions centered on Voyager 1's FDS, a critical computer component responsible for collecting information from all of the spacecraft's scientific instruments and engineering sensors. This subsystem normally processes data from 11 different scientific instruments, monitors the health of various spacecraft systems, and formats everything into organized packets for transmission back to Earth. When the FDS began malfunctioning, it effectively cut off communication between Voyager 1's instruments and mission controllers, leaving scientists blind to what the spacecraft was observing in interstellar space. Conventional resets failed, leading to a months-long effort to isolate a single corrupted memory chip. Mission controllers found themselves facing a particularly frustrating paradox, because Voyager 1 appeared to be functioning normally in every measurable way except for its data transmissions. The spacecraft maintained proper orientation with its antenna pointed accurately toward Earth. Its nuclear power source continued providing steady electricity to all systems, and its internal temperature regulation systems kept critical components within acceptable operating ranges. All engineering telemetry suggested that Voyager 1 was healthy and operating according to its programmed instructions, yet the scientific data it was supposed to be collecting remained completely inaccessible due to the communication breakdown. The 22-hour communication delay between Earth and Voyager 1's current position made real-time diagnosis impossible and transformed every troubleshooting attempt into a multi-day process. When engineers identified a potential solution and transmitted commands to implement it, they had to wait nearly 2 full days to learn whether their approach had been successful. This extended timeline meant that what might normally be resolved in hours or minutes for satellites in Earth orbit became a weeks-long investigation for Voyager 1. The communication anomalies persisted for over 5 months, creating the longest period of data interruption in Voyager 1's entire mission history. During this time, the spacecraft continued its journey deeper into interstellar space while scientists remained unable to access the unprecedented measurements it was collecting about conditions in the region between stars. This data loss represented a significant setback for interstellar research because Voyager 1 serves as humanity's only direct probe of the space environment beyond our solar system's protective boundary. Mission controllers sent a specialized command called a poke to the FDS on March 3, 2024 to run different software sequences and isolate the exact location of the corrupted memory. This diagnostic procedure confirmed that approximately 3% of the FDS memory had been corrupted, but this small portion of damaged storage was critical enough to prevent the entire computer from carrying out its normal data processing operations. Engineers eventually traced the source of the communication problems to a corrupted memory chip within the flight data subsystem that had been damaged by either a high-energy cosmic ray particle or simply the effects of aging after nearly 5 decades of operation. The technical solution involved relocating the affected software code from the corrupted memory chip to other available storage locations within the FDS. This process was complicated by the fact that no single alternative location had enough space to hold all of the displaced code, forcing engineers to divide the software into sections and distribute them across multiple memory locations. Each relocated code section required careful modification to ensure it would still function properly when separated from its original location, and all references to the code's memory addresses throughout the flight data subsystem had to be updated to reflect the new storage arrangement. By April 2024, mission controllers successfully restored normal communications with Voyager 1, allowing the spacecraft to resume transmitting coherent engineering data about its health and status. The team confirmed that all systems appeared to be operating properly, and within weeks, scientific data began flowing again from humanity's most distant explorer. However, this triumph over the FDS corruption would prove to be only the beginning of a new series of puzzling anomalies that would soon challenge everything engineers thought they understood about spacecraft operations in interstellar space. The attitude control mystery. In early 2025, Voyager 1's attitude articulation and control system began exhibiting behavior that defied every principle of spacecraft engineering that NASA scientists had learned over 5 decades of space exploration. This critical system serves as the spacecraft's navigation brain, constantly monitoring Voyager 1's position in 3-dimensional space and making precise adjustments to keep the probe's high-gain antenna pointed directly at Earth. Without this system functioning properly, the spacecraft would tumble through interstellar space like a lost piece of debris, unable to communicate with mission control or transmit the scientific data it continues collecting from beyond the solar system. The AACS operates through a network of gyroscopes, star trackers, and thruster systems that work together to maintain Voyager 1's orientation with remarkable precision across the 24.5 billion kilometer distance to Earth. The system must account for tiny forces that gradually alter the spacecraft's attitude, including pressure from solar radiation, gravitational influences from distant objects, and even the slight thrust produced by heat radiating from the spacecraft's nuclear power source. These corrections require accuracy measured in fractions of degrees, because even the smallest pointing error would cause Voyager 1's narrow antenna beam to miss Earth entirely and sever communication with the spacecraft forever. Engineers first noticed the attitude control anomalies when the system began transmitting status reports that contained completely impossible data values. The AACS was sending information indicating that the spacecraft was oriented in positions that violated the basic laws of physics, with readings suggesting that Voyager 1 was somehow pointing in multiple directions simultaneously. These measurements appeared to show the spacecraft's antenna aimed at locations in space where no stars existed, while other readings indicated orientations that would have made Earth-based communication impossible. The most puzzling aspect of this malfunction was that Voyager 1's antenna continued functioning perfectly throughout the entire period when the AACS was transmitting corrupted data. Mission controllers received clear, strong signals from the spacecraft without any indication that communication problems were affecting the actual transmission process. The high-gain antenna remained locked onto Earth with the same precision it had maintained for decades, suggesting that the attitude control system was performing its primary function correctly while simultaneously reporting status information that made no logical sense. The AACS reported impossible orientations, while actual signal strength and deep space network link quality confirmed Voyager 1 maintained correct pointing. Engineers analyzing these transmissions found sequences that seemed to indicate the spacecraft was experiencing rotation rates that would have been catastrophic, followed immediately by readings suggesting perfectly stable orientation. Some data packets contained measurements that placed Voyager 1 simultaneously above and below the ecliptic plane, creating mathematical contradictions that no real spacecraft could produce. The randomness of these data patterns became even more concerning when engineers realized that the corrupted information wasn't following any predictable sequence or error pattern that might indicate a specific component failure. Traditional spacecraft malfunctions usually produce recognizable signatures that point toward particular systems or components that need attention. The AACS anomalies generated what appeared to be completely arbitrary data that provided no clues about what might be causing the system to report impossible measurements while continuing to function normally. Mission controllers attempted to run diagnostic routines specifically designed to test the attitude control system sensors and processing components, but these procedures returned results that were equally contradictory. Some diagnostic tests indicated that all AACS components were functioning within normal parameters, while other tests suggested that critical sensors were providing readings that couldn't possibly be accurate. The system would pass certain diagnostic checks perfectly, while simultaneously failing others in ways that made no engineering sense given the interconnected nature of the attitude control components. The fault protection systems aboard Voyager 1 remained completely inactive throughout the entire period when the AACS was transmitting corrupted data, adding another layer of mystery to the situation. These automatic safety systems are designed to detect anomalous behavior in critical spacecraft systems and trigger protective responses to prevent permanent damage to the probe. The fact that no fault protection sequences activated suggested that the spacecraft's internal monitoring systems couldn't detect anything wrong with the attitude control system, even though the data being transmitted to Earth was clearly corrupted. Engineers discovered that the AACS continued to execute all of its programmed attitude control maneuvers correctly despite the data transmission problems. The system maintained proper spacecraft orientation during scheduled communication sessions, adjusted pointing direction to compensate for Voyager 1's motion through space, and responded appropriately to commands sent from mission control. These observations indicated that the physical hardware responsible for attitude control was operating normally, while only the data reporting functions were producing impossible readings. Temperature sensors within the AACS reported stable operating conditions throughout the malfunction period, ruling out thermal effects as a potential cause of the data corruption. The system's power consumption remained constant at expected levels, and voltage measurements showed no fluctuations that might indicate electrical problems affecting the attitude control computers. All environmental monitoring systems suggested that the AACS was operating in a benign environment where no external factors should have been capable of causing the observed data anomalies. The contradiction between the AACS, perfect performance, and corrupted data transmissions created a situation that challenged fundamental assumptions about how spacecraft systems fail in the deep space environment. Engineers had extensive experience with various types of attitude control problems, ranging from sensor degradation to computer processor failures, but none of these familiar failure modes produced the specific combination of normal operation and impossible data readings that Voyager 1 was exhibiting. The ongoing nature of the AACS anomalies has forced mission planners to develop new operational procedures that account for the possibility that attitude control data transmissions might not accurately reflect the spacecraft's actual status. Controllers now rely more heavily on signal strength measurements and communication link quality to assess Voyager 1's pointing accuracy, rather than trusting the attitude data that the AACS continues to transmit. This unprecedented situation has left NASA's most experienced engineers searching for explanations that could account for such contradictory behavior in a spacecraft that has operated reliably for nearly 5 decades. Radiation, age, or something else. Scientists examining these contradictory behaviors have developed several competing theories about what might be causing Voyager 1's mysterious data transmissions. The leading explanation centers on the simple fact that Voyager 1 has been operating in the harsh environment of space for nearly 48 years, far exceeding its original design lifetime of just 5 years. During this unprecedented operational period, the spacecraft has been bombarded by cosmic radiation, exposed to extreme temperature variations, and subjected to conditions that no Earth-based testing facility could adequately simulate when the probe was built in the 1970s. The most immediate concern involves the gradual degradation of electronic components that have been functioning continuously for almost 5 decades without any maintenance or replacement. Computer chips, memory storage devices, and circuit boards aboard Voyager 1 were manufactured using 1970s technology that relied on much larger transistor designs and less sophisticated radiation hardening techniques compared to modern spacecraft electronics. These older components were built to tolerate radiation exposure for the planned 4-year mission duration, but they have now endured more than 10 times their intended operational lifespan in an environment where high-energy particles constantly assault their crystalline structures. Memory storage systems represent a particularly vulnerable component category because they rely on maintaining precise electrical charges across microscopic storage cells that can be disrupted by cosmic ray impacts. A single high-energy particle striking a memory chip can flip individual bits from one state to another, corrupting the stored information and causing computer systems to execute incorrect instructions or report invalid data. The CMOS memory technology used in Voyager 1's computers is especially susceptible to these bit flip errors because the charge levels that distinguish between digital ones and zeros can be altered by relatively low energy particle strikes. The corrupted memory chip that caused Voyager 1's communication breakdown in 2023 demonstrates how even minor component failures can cascade into major system malfunctions when dealing with the complex interdependencies of spacecraft computer architectures. The radiation environment in interstellar space creates conditions that were largely theoretical when Voyager 1 was designed and launched. Beyond the protective boundary of our solar system's heliosphere, the spacecraft encounters cosmic rays from distant supernovae and galactic sources that carry energy levels far exceeding anything found within the solar system. These high-energy particles can penetrate spacecraft shielding and interact with electronic components in ways that produce subtle but cumulative damage over extended time periods. The constant bombardment of cosmic radiation gradually alters the electrical properties of semiconductor materials, potentially causing circuits to behave differently than their original specifications. Power generation aboard Voyager 1 faces its own aging challenges as the spacecraft's plutonium-238 radioisotope thermoelectric generator experiences natural radioactive decay. The RTG's power output decreases by approximately 0.79% each year as the plutonium-238 fuel undergoes its natural decay process, with a half-life of 87.74 years. This gradual power reduction forces mission planners to make increasingly difficult decisions about which systems to keep operational as available electricity continues declining. The decreasing power supply compounds other aging effects because systems operating at lower voltages become more susceptible to interference from cosmic radiation and may not function as reliably as they did when receiving full power. Charged particle interactions with Voyager 1's electronics occur on a scale that makes them nearly impossible to predict or prevent using conventional spacecraft design techniques. Individual cosmic ray particles carry enough energy to disrupt multiple circuit elements simultaneously, creating complex failure modes that don't follow the predictable patterns associated with normal component aging. These particle strikes can cause temporary glitches that reset themselves automatically, permanent damage that accumulates over time, or intermittent problems that appear and disappear without any apparent pattern. Temperature cycling effects compound the radiation damage by causing expansion and contraction of electronic components that gradually loosens connections and creates microscopic fractures in circuit materials. Voyager 1 experiences temperature variations as it moves through regions of interstellar space with different thermal characteristics, and these changes stress components that have already been weakened by decades of radiation exposure. The combination of thermal stress and radiation damage creates aging patterns that were impossible to test adequately during the spacecraft's original development period. The challenge of diagnosing Voyager 1's problems is complicated by the fact that scientists have no other data sources for comparison in the interstellar environment where the spacecraft operates. Unlike missions within the solar system, where multiple spacecraft have explored similar regions and provided comparative measurements, Voyager 1 represents humanity's only direct probe of conditions in local interstellar space. This isolation means that researchers cannot determine whether the spacecraft's anomalous behavior reflects problems with the probe itself or normal variations in the interstellar environment that affect electronic systems in unexpected ways. Mission engineers with decades of deep space experience acknowledge that Voyager 1's recent signal anomalies present diagnostic challenges unlike anything they have encountered during their careers. The combination of extreme distance, communication delays, aging 1970s technology, and unknown environmental conditions creates a troubleshooting scenario that pushes beyond the boundaries of established engineering practices. Traditional diagnostic approaches that rely on rapid testing cycles and immediate feedback become nearly impossible when each command sequence requires over 40 hours to complete. The expertise required to understand Voyager 1's current problem spans multiple scientific disciplines, from radiation physics and materials science to computer engineering and interstellar astronomy. Researchers must consider how cosmic ray interactions affect semiconductor devices, how thermal cycling degrades circuit connections, and how software designed in the 1970s responds to hardware failures that its programmers never anticipated. This interdisciplinary complexity means that no single expert or research team possesses all the knowledge needed to definitively explain the spacecraft's mysterious behavior, forcing NASA to mobilize its most experienced specialists for an unprecedented troubleshooting effort. NASA's response and troubleshooting efforts. The JPL team responsible for maintaining contact with humanity's most distant spacecraft operates from a specialized facility in Pasadena, California, where banks of computer monitors display telemetry data arriving from 24.5 billion kilometers away. These engineers possess decades of experience managing deep space missions, but Voyager 1's recent behavior has presented them with diagnostic challenges that push far beyond anything they encountered during their careers working with spacecraft in more conventional orbital environments. The diagnostic procedures required to investigate Voyager 1's problems must account for the 45-hour round-trip communication delay that makes real-time troubleshooting impossible. Engineers cannot simply run quick tests or request immediate status updates like they would for satellites orbiting Earth or even probes exploring the outer planets of our solar system. Every command sequence sent to Voyager 1 requires careful planning and consideration because mission controllers must wait nearly 2 full days to learn whether their instructions were received and executed properly. This extended timeline transforms simple diagnostic procedures into week-long investigations where each step must be planned meticulously in advance. Communication with Voyager 1 depends entirely on Deep Space Station 43, the 70-meter radio dish located in Canberra, Australia, which serves as the only antenna on Earth powerful enough to send commands across the vast distance to the spacecraft. This single point of contact creates a critical vulnerability in maintaining the communication link, especially when the antenna requires maintenance or upgrades that temporarily sever the connection with humanity's most distant explorer. The reliance on one facility emphasizes the delicate nature of operations at such extreme distances where backup options simply do not exist. Mission planners have adapted operational protocols that were originally developed in the 1970s to work with modern troubleshooting techniques and diagnostic capabilities. The original procedures assumed that engineers would have rapid feedback from spacecraft systems and could iterate quickly through different approaches to solve technical problems. Current operations require a completely different methodology where engineers must predict potential outcomes for each command sequence and prepare contingency plans for various scenarios before transmitting instructions to the distant spacecraft. The team uses sophisticated computer simulations to model how Voyager 1 systems should respond to different diagnostic commands, allowing them to anticipate potential problems before sending instructions across the vast distance to the spacecraft. These simulations incorporate decades of operational data about how Voyager 1's components have behaved under various conditions throughout its long mission. Engineers can test their troubleshooting approaches virtually before committing to the lengthy process of implementing them on the actual spacecraft operating interstellar space. Power conservation has become a critical factor in every decision about diagnostic procedures because Voyager 1's nuclear power source continues to decline by approximately 4 watts each year. The spacecraft currently operates on less than 300 watts of electrical power, roughly equivalent to 3 bright light bulbs. Yet this limited energy must support all scientific instruments, communication systems, computer operations, and attitude control functions. Every diagnostic test consumes precious power that could otherwise be used for scientific observations or essential spacecraft operations. Historical data analysis plays a crucial role in understanding Voyager 1's current behavior because engineers can compare recent telemetry with patterns recorded throughout the spacecraft's 48-year journey. The mission database contains millions of measurements from every system aboard Voyager 1, creating a comprehensive record of how the spacecraft has performed under different conditions and operational modes. Engineers search through this vast archive looking for similar patterns or gradual trends that might explain the current anomalies. The expertise required to troubleshoot Voyager 1's problems spans multiple generations of aerospace engineers because the spacecraft was built using technologies that are no longer taught in modern engineering programs. Veteran engineers who participated in the original mission design work alongside younger team members, sharing irreplaceable knowledge about the spacecraft's internal systems and operational characteristics. This collaboration between experienced specialists and newer engineers proved essential during the 2024 effort to relocate corrupted software code within the flight data subsystem. The successful resolution of the 2023 communication breakdown demonstrated how multiple engineering teams can work together to develop creative solutions for unprecedented problems. Each team independently verified command sequences before transmission, checking for potential conflicts with other spacecraft systems and ensuring that instructions would not exceed power consumption limits. The collaborative approach included extensive simulations that predicted how Voyager 1 should respond and contingency plans for various scenarios that might occur during command execution. Software-based workarounds have become the primary tool for addressing Voyager 1's recent problems because they can be implemented remotely without requiring any physical modifications to the spacecraft. The 2024 patch that relocated corrupted software code to different memory locations within the flight data subsystem required engineers to understand the spacecraft's memory architecture in detail and carefully modify software while ensuring that relocated code continued to function properly in its new storage locations. Every command sent to Voyager 1 undergoes extensive review and approval processes because mistakes could permanently damage the spacecraft or sever communication links forever. The approval process includes multiple independent reviews by different engineering teams, comprehensive simulations, and detailed analysis of potential risk and benefits. This methodical approach reflects the irreplaceable nature of Voyager 1's position and the impossibility of physical repair missions at such extreme distances. The ongoing troubleshooting efforts represent a race against time, as Voyager 1's power continues declining and the spacecraft faces an uncertain future operating with aging components in the harsh environment of interstellar space. Despite these technical challenges, the spacecraft continues to fulfill its primary scientific mission, collecting unprecedented measurements from a region of the interstellar data revolution. These measurements continue revealing groundbreaking discoveries about the space between stars, with Voyager 1's instruments still operational and detecting phenomena that no Earth-based telescope could ever observe directly. The cosmic ray detector, magnetometer, and plasma wave instrument remain functional according to NASA's tracking systems, providing the only direct measurements humanity possesses of conditions in interstellar space. Every data packet that successfully reaches Earth advances our understanding of galactic structure and composition in ways that cannot be replicated by any other means. The cosmic ray detector aboard Voyager 1 has recorded radiation levels in interstellar space that demonstrate a 100-fold increase in electron density compared to measurements taken within our solar system's protective boundary. These high-energy particles originate from distant supernovae, stellar explosions, and other violent galactic events that accelerate charged particles to tremendous velocities as they travel across vast distances through space. The detector measures cosmic ray intensities that provide scientists with direct evidence of the energetic processes that shape the interstellar environment and influence the evolution of nearby stellar systems. Particle measurements from Voyager 1 have revealed that interstellar space contains a complex mixture of hydrogen atoms, helium nuclei, and heavier elements that were expelled by dying stars throughout the galaxy's history. The spacecraft's instruments detect these particles as they stream past at velocities of hundreds of kilometers per second, carrying chemical signatures that tell the story of stellar evolution and galactic recycling processes. Scientists analyze the composition and energy distribution of these particles to understand how elements created in stellar cores are distributed throughout the galaxy and eventually incorporated into new star systems. The magnetometer instrument continues measuring the interstellar magnetic field with precision that allows scientists to map the large-scale magnetic structure of our local galactic neighborhood. These measurements show that the magnetic field in interstellar space is much more organized than theoretical models had predicted, with field lines that appear to be aligned with the overall structure of the galaxy's spiral arms. The magnetic field strength averages approximately 5 microgauss, which is about 100,000 times weaker than Earth's magnetic field, but still strong enough to influence the motion of charged particles across interstellar distances. Plasma wave measurements from Voyager 1 provide unique insights into how charged particles interact with the interstellar magnetic field to create waves and oscillations in the surrounding space environment. The spacecraft's plasma wave instrument detected an 80-fold jump in plasma density following a solar outburst, demonstrating the instrument's capability to measure how disturbances from our sun propagate into interstellar space. These measurements help scientists understand how energy and matter move through the space between stars and how stellar winds from distant sources interact with the general galactic environment. Temperature measurements in interstellar space have surprised scientists because they reveal a medium that is simultaneously very hot and very cold, depending on which particles are being measured. The overall kinetic temperature of the interstellar gas reaches approximately 15,000 degrees Celsius, yet the low particle density means that the actual thermal energy content is extremely small. Individual particles carry enormous kinetic energies that reflect the violent processes that ejected them from their stellar origins, while the sparse distribution of these particles creates an environment that would feel incredibly cold to any object placed within it. Density measurements from Voyager 1 indicate that interstellar space contains approximately 0.04 atoms per cubic centimeter, making it far more empty than the best vacuum that can be created in Earth-based laboratories. This extreme emptiness means that particles can travel for thousands of years without colliding with other atoms, allowing them to preserve information about the stellar processes that created them. The low density also means that pressure waves and disturbances can propagate across vast distances without being absorbed or scattered by intervening matter. The spacecraft's observations are revealing how solar activity affects conditions in interstellar space through measurements of pressure pulses that originated from coronal mass ejections on our Sun. Scientists are seeing pressure pulses move past the spacecraft from events on our Sun, demonstrating how the Sun interacts with the interstellar environment far beyond the traditional boundary of the solar system. These measurements show that our Sun's influence continues to affect the surrounding interstellar medium through shock waves that travel outward at high velocities. Voyager 1's unique position allows it to study how charged particles from our solar system interact with those emitted by other nearby stars, creating a complex mixing zone where different stellar winds collide and merge. The spacecraft detects particles that originated from multiple stellar sources, each carrying distinctive energy signatures and chemical compositions that reflect the different types of stars that produce them. These observations provide direct evidence of how matter and energy circulate through the local galactic environment and how stellar populations influence the properties of surrounding space. Recent discoveries about the structure of the heliosphere boundary have emerged from Voyager 1's measurements as it crossed from solar-influenced space into the true interstellar medium. The spacecraft detected a transition region that was thicker and more complex than scientists had predicted, revealing multiple layers where solar and interstellar particles mix in varying proportions. These boundary measurements help scientists understand how our solar system moves through the galaxy and how stellar winds from other stars might affect planets in distant solar systems. The ongoing data collection faces increasing risks as Voyager 1's signal anomalies threaten to disrupt the transmission of scientific measurements that cannot be replicated by any other means. The spacecraft's location becomes more scientifically valuable with each passing day as it encounters conditions that vary across different regions of the local interstellar medium. However, the window for collecting this unprecedented data may be closing faster than anyone anticipated. The race against time. Voyager 1's nuclear power source presents mission controllers with an unforgiving countdown that grows more critical with each passing day as this spacecraft ventures deeper into interstellar space. The 3 radioisotope thermoelectric generators that have powered the probe for nearly 48 years continue their relentless decay, producing approximately 4 watts less electricity each year as the plutonium-238 fuel naturally breaks down according to its 87.74-year half-life. When Voyager 1 launched in 1977, these nuclear batteries generated 470 watts of electrical power. The current output has dropped to just 220 watts, representing less than half of the spacecraft's original power capacity. This steady decline in available electricity forces NASA engineers to make increasingly difficult decisions about which systems to keep operational and which must be sacrificed to extend the mission's remaining lifetime. The power generated by Voyager 1 must support all scientific instruments, communication systems, computer operations, attitude control functions, and essential heating elements that prevent critical components from freezing in the absolute cold of interstellar space. Every watt of electricity represents precious operational capability that cannot be replaced or restored once the nuclear fuel continues its inexorable decay process. Mission planners use sophisticated computer models to predict how much power various spacecraft systems will consume under different operational scenarios. But the age of Voyager 1's components introduces uncertainty factors that make precise calculations challenging. Hardware that has operated for nearly 5 decades doesn't always behave according to original specifications, and power consumption patterns can vary unpredictably as components age and their electrical characteristics change. Engineers must account for these uncertainties when planning power allocation strategies that could determine whether critical systems remain functional for months or years. The systematic shutdown of spacecraft systems began decades ago when mission controllers turned off Voyager 1's imaging system in 1990 after completing its primary planetary exploration objectives. The Plasma Science instrument followed in February 2007, marking the beginning of an accelerating process of power conservation that now defines every operational decision. The team responsible for managing Voyager 1's power budget has already begun shutting down additional instruments and systems to conserve electricity for the most scientifically valuable operations. Heaters that once protected non-essential components from temperature extremes have been turned off, allowing those systems to operate at colder temperatures that reduce their operational lifetime but preserve power for more critical functions. The spacecraft's fields and particles instruments receive priority for continued operation because they are most likely to transmit valuable data about interstellar space conditions that cannot be obtained through any other means. Engineers are already planning to shut down Voyager 1's low-energy charged particle instrument in 2026 as part of a systematic approach to extending the mission's operational timeline. This decision represents a significant loss of scientific capability because the instrument provides unique measurements of particle interaction in interstellar space, but the power savings will allow other instruments to continue operating for additional years. Current projections indicate that Voyager 1 will retain enough power to operate at least one scientific instrument into the 2030s, with engineering data potentially continuing until approximately 2036, when the RTG power output drops below critical thresholds. These estimates depend on the spacecraft's ability to maintain efficient power management without experiencing additional system failures. The recent signal anomalies and communication problems have complicated these calculations because troubleshooting efforts require activating systems that normally remain in standby mode to conserve energy. The current signal problems could potentially accelerate the end of Voyager 1's mission if they require extensive troubleshooting efforts that consume significant amounts of power. Diagnostic procedures involve activating computer systems, running software routines, and transmitting additional commands that increase the spacecraft's overall power consumption beyond normal operational levels. If engineers cannot resolve the communication anomalies efficiently, the additional power requirements for ongoing troubleshooting could force earlier shutdowns of scientific instruments and reduce the mission's total operational timeline. NASA faces the challenging prospect of balancing immediate problem-solving efforts against long-term mission preservation as Voyager 1's power reserves continue diminishing. Every command sent to diagnose the mysterious signal patterns requires careful evaluation of its power consumption, impact, and potential scientific value compared to maintaining normal operations. Mission planners must weigh the importance of understanding the current anomalies against the risk of shortening the overall mission duration through excessive power usage during troubleshooting activities. The urgency of resolving Voyager 1's communication problems becomes more apparent when considering that this may represent humanity's last opportunity to receive direct measurements from interstellar space for decades or possibly centuries. No other spacecraft currently exists with the capability to reach interstellar space within the next several decades, and the advanced propulsion technologies needed to build faster interstellar probes remain in early development stages. Voyager 1's unique position beyond the solar system's boundary makes every day of continued operation irreplaceable for advancing scientific understanding of the galaxy beyond our sun's influence. Mission controllers recognize that they are managing the final phase of what may be the most important space exploration achievement in human history. The scientific data that Voyager 1 continues collecting represents the only direct observations humanity possesses of conditions in the space between stars, and the loss of this capability would leave researchers dependent on remote observations from Earth-based telescopes for understanding interstellar phenomena. The spacecraft's location becomes more scientifically valuable with each passing day as it encounters new regions of interstellar space with potentially different characteristics and compositions. The race against time intensifies as engineers realize that Voyager 1's remaining operational period may be measured in years rather than decades, depending on how successfully they manage the spacecraft's declining power resources. The nuclear fuel that has powered the probe through its epic journey to the edge of the solar system will eventually reach levels too low to maintain critical systems, forcing an end to the longest-running space mission in history. Every successful data transmission from Voyager 1 represents a victory against the fundamental physics of radioactive decay that will ultimately silence humanity's most distant messenger. These power management challenges and mysterious signal anomalies have transformed Voyager 1's final years into something far more complex than anyone anticipated when the spacecraft first crossed into interstellar space. The implications of these technical challenges extend far beyond troubleshooting procedures for a single spacecraft. Voyager 1's mysterious signals from 24.5 billion kilometers away represent more than just technical problems with aging spacecraft systems. These anomalies highlight both the incredible achievement of maintaining contact with 1970s technology across interstellar distances and the ongoing challenges of exploring regions where no human-made object has ever operated before. The spacecraft continues pushing boundaries that seemed impossible when it launched nearly 5 decades ago, proving that human ingenuity can overcome obstacles that appear insurmountable. As Voyager 1 ventures deeper into interstellar space than any probe before it, still transmitting precious data, despite 46 years of operation, it has redefined our place in the cosmos and will continue to whisper secrets from the stars until its